Welcome back, everybody. Today I'm going to be going over a slightly different way to use an LMC material modifier. And let's just jump right into it. This video idea is based off of a part that I had seen working with a company. And before we get into it, I'll just review what LMC is traditionally used, or how LMC is traditionally used. So LMC is typically taught as a material modifier that is there to control a wall thickness. Let's say we had a part with a hole and we don't want to get some super thin wall condition because that hole is pressurized. Well, typically we'll apply some sort of LMC positional tolerance to the axis of the part, let's say. So in this case, I've applied just arbitrarily a 0 at LMC positional tolerance. And that means that when the feature is at its LMC condition, so the largest the hole can be, as in, LMC least material condition means like the lightest part that you can get, it is allowed 0 positional tolerance. And then as it moves from its LMC position towards its MMC position, it gains positional tolerance based off of the size of the part. And how do we know what the size of a hole is when we're talking about LMC? Well, it's a little bit different when you look at LMC versus MMC or RFS. With LMC, you look at the actual minimum material envelope of the feature. So we take a perfect counterpart and contract it about the hole until it makes full contact. And the diameter of that actual minimum material envelope is the measured diameter. So let's say we have some minimum wall condition that we want to protect based off of like an FEA or something. We apply this 0 at LMC positional tolerance. That combination of controls between the size and the positional tolerance creates what's called a virtual condition, and the feature is not allowed to violate that virtual condition. So the measured feature, the real feature, is not allowed to go beyond that virtual condition. And with that out of the way, let's look at how I used LMC in this case study I'm going to be talking about. So what we had was a housing and a rotating shaft running through the middle of it, and there was seals on either side of this cavity, and bearings were supporting the shaft. Some sort of fluid was running through the center cavity, and the design team wanted to keep the fluid from entering the bearing cavity area. Of course, we don't want the shaft to come in contact with the sidewalls. So, that's I think the first place that a lot of people would go. So why would I be talking about this in an LMC video? Because this is clearly something we should be controlling with MMC, because we want at that maximum material condition, when the hole is the smallest, we want to make sure it's well positioned so it doesn't contact the shaft. And that's true. However, if you've ever worked with seals, you also know that there's something called an E-gap. So there is a gap between the shaft and the housing, and if it's too large and the pressure is too high, that seal can extrude through that gap, and then you lose your sealing boundary. And in a lot of ways, this is actually slightly worse than if you violated the MMC condition, because if you made that shaft, or you made that bore too small and too out of position, well, you might not be able to assemble it. But if you make that hole too big, or too big and then slightly off center, and there's an E-gap that gets too large, well, then you can assemble the part, but you could still get a condition where you extrude that seal, which could damage the whole assembly. So there might not be much chance for rework on that. So let's look at sort of the drawing that I was presented with, and I'm simplifying it a little bit because we're going to assume that the shaft was perfect form and perfect 45 millimeter diameter across the sort of the seal interface. So the starting point, we had these two 80 millimeter bores, and they were both toleranced for interference widths with the bearing race. They had together a datumless positional tolerance for the two coaxial 80 millimeter bores. and this was based off of the alignment that was required for the bearings, I believe. And then 4 times these 45 millimeter diameters with a positional tolerance to AB. So this reflected the requirements of the part really, really well. I was pretty impressed with this. Where it started to get tricky was when the tolerances were starting to be applied to those 4 45 millimeter bores. The machine shop that they were working with sort of influenced them a little bit and said, we can hit 2 thou, which is about 50 microns positional tolerance to these datums. So they said, okay, we'll use a 2 thou positional tolerance. And then the engineers wanted a 1 thou gap at least. So that's 25 microns. So you could take that 45 millimeters and you say, oh, we need 25 microns on either side. And then you also have to look at the positional tolerance. So if you were just looking at the minimum or the inner boundary, you'd have 45.05, but then you have to add that positional tolerance as well, because we have that 50 microns that the bores are allowed to move. So you do 45.05, which is the minimum boundary, or the inner boundary, and you add that positional tolerance, and then you get 45.1 millimeters. So that's the smallest, or the maximum material condition is 45.1. Then the final piece of the puzzle is the least material condition, so the largest the hole can be. The seal manufacturer said they could handle a 4 thou extrusion gap, which is about 0.1, and then so 0.1 on either side of the bore is 45.2, but then again we need to subtract, in this case, the positional tolerance, which gives us 45.15. So they had a size tolerance of 50 microns, a positional tolerance of 50 microns, and this is starting to get really tight. And then you factor on top of it that the shaft was not actually perfect in this assembly, and you start eating into either your size tolerance or your positional tolerance. So that's a really tricky situation to be in. So they were right at the limits for the machine shop. They were getting a high scrap rate, and again, these numbers were getting reduced with the tolerance of the shaft included. So how did we do this? So let's look at this on a graph. We have a 50 micron tolerance band across the size range that they gave. Is there a way that we can get more tolerance out of this? Let's start over. Let's look at this in terms of inner and outer boundaries. So we established that the inner boundary was 45.05, and that was based off of the clearance that they needed from the shaft, and then the outer boundary was 45.2. That was based on the extrusion gap. So let's start there. What if we were to look at this in terms of a MMC assembly? Well, the way to get the most positional tolerance and the most size tolerance out of an assembly is to do things at 0 or with a 0 at MMC positional tolerance. So let's do that, and then let's take a look at the graph. And this entire area is now given to us in terms of size and positional tolerance. So this is obviously a much larger area than just this constant 50 micron positional tolerance. However, once we hit, if you do the math, 45.125 millimeter size bore, the combination of positional tolerance and size tolerance would actually allow for an extrusion gap larger than we want. So let's look now at the boundaries again, and then maybe we try adding a 0 at LMC as well. So that way we're not violating that 45.2 millimeter boundary. And then we look at the line that would create, and that LMC line would allow for all of this area under here, but again at that 45.125 millimeter bore size, you might end up with a condition where the shaft ends up contacting the housing. But if we work and if we use both of those together, something cool happens. So this is the area, the size, and positional tolerance that was allowed before. But if we have both the LMC and the MMC at 0 simultaneously used, that creates a condition where we actually get all of this area. So if you were to only measure it at LMC, you would get a little bit of extra area, and the CMM, or however you're measuring this, would pass the part. But the MMC condition would then be violated. So anything in here would be fine for LMC, but for MMC, that would end up throwing up a flag. And then likewise, for this side, the MMC would pass, and then the LMC condition would end up throwing up a flag. But you look at all this extra tolerance you get, both in size and position. And this is the kind of cool stuff that you can do when you start looking at things in terms of boundaries. So instead of using LMC in this case to control a thin wall, we actually used it to control an edge gap, which I think is a pretty cool way to use LMC. Anyways, hopefully someone got something out of this video. Make sure to reach out to me over on my website if you have GD&T questions about this. There's a contact me page, and have a good one.